This is joint work between Graz University of Technology and Fraunhofer Isaac in Munich. As you can see from the title, this work is about finding address-based side channel leakage in program binaries. Sorry. So let's dive into the topic. What is exactly side channel leakage? Well, suppose that Alice emails with her friend. She securely encrypts her email before sending it out into the ether. And for now, let's ignore potential attacks on SMIME and BGP as we have heard previously. When looking closer at what happens inside a computer, we see that there's some information leaking during the computation, that is, during encryption or decryption. And we call this side channel leakage. And if enough information is leaked, then an attacker can maybe guess, infer the secret key, which is bad because he can decrypt all past and future communication in the worst case. So it's very important to avoid side channel leakage in your source code. So what exactly is address leakage? Address leakage occurs whenever a secret information is somehow leaked through memory access patterns, that is, through memory accesses. Memory addresses. Secret information can be anything from text messages to passwords to cryptographic keys, etc. And memory accesses somehow depend on this secret. So we say that there is a secret dependency, a dependency between secret input and memory addresses output. So how does this look like in practice? Well, we know two root causes for address leakage. First, data leakage, which occurs whenever the secret is used to compute data addresses. In the example on the left, the secret is used as index into a lookup table T. And during runtime, this will translate to a data access in which the accessed address depends on the secret. On the other hand, we have control flow leakage, which occurs whenever a secret is used in a condition. Thus, different code gets executed for different secrets. For example, when a secret condition is true, the function left gets executed. If false, the function right gets executed. So by just observing which code gets executed, an attacker can infer the secret. So now that we know what address leakage is, let's look at how we can exploit this in practice. When we have a look at modern CPUs, there are plenty of components like complex memory hierarchies, branch prediction, etc., which all share some form of memory between different programs, and this resource sharing creates side channels. For example, an attacker process might use two cache lines in the shared caches. And let's now assume that Alice has a control flow leak, as in the previous example on the right side here. So she accesses the left cache line when the secret condition is true and the right cache line otherwise. So in our example, the secret condition is true, so Alice accesses the left cache line. And the attacker's data, which was previously there, gets displaced to DRAM. So now when the attacker accesses the right cache line, this one is fast, a fast access, because data is in the cache. But when he accesses the left cache line, this is slow, because the attacker's data has to be first loaded from DRAM. So by mere timing measurement, the attacker can learn which cache line Alice accessed. And he can infer that the secret condition was true. So this is an example of address leakage, how you can exploit it via shared caches. But in practice, there are many more components like DRAM, etc., which all leak some form of address information. And we do not give details about all those components, but it's important to understand that the term address leakage captures all of them. So what did we do? First, our objective is we want to analyze a program and want to find as many address leaks as possible with constrained resources and limited developer effort. So we want to be efficient. So how do we achieve this? First, we have to decide between two methods for finding address leaks, namely static and dynamic analysis. So this is only a very coarse-grained overview here. There's certainly methods in between also. Static analysis typically symbolically evaluates all program paths. And that way they can compute upper leakage bounds. They can achieve 0 false negatives. They can prove absence of leaks in some cases. However, there are certain problems because they suffer from imprecision, which yields false positives, which prohibits analysis of interpreted code, for example. And also the symbolic execution is quite expensive. It does not scale to large programs. In contrast, dynamic analysis can use a concrete execution, real execution, and it only reports real address leaks. So we can achieve 0 false positives. And that's what we want to have. However, the main problem with dynamic methods is that they suffer from false negatives. That is, they might miss leakage, which is not found. So it's very important to reduce false negatives in this case. Okay, and we will use dynamic analysis because it gives us several practical benefits for analyzing real-world software. So let's come to our contribution. Data, differential address trace analysis. What did we do? We designed and implemented a dynamic leakage detection tool, which we call data. How does it work? First, the user specifies which information is secret. For example, a cryptographic key or some messages. Then the tool will automatically find arbitrary address-based side channel leaks in the program binary. Also, since not all leaks are equally dangerous in practice, we have one more step where the tool uses statistical tests known from the hardware side channel literature to test how much information is actually leaked. Our tool can detect arbitrary address leaks, that is, data leaks and control flow leaks, which captures all address-based attacks we saw before. And we achieve good results by lowering both false positives and false negatives. We filter out non-deterministic program behavior, which is common for asymmetric ciphers, as we saw before, RSA blinding. That is, we filter leaks that are independent of the secret. And data, our approach is practical into several directions. First, it's fully automated. That is, there's no developer annotations needed in the source code. We even don't need source code for the analysis. And our tool is fast and openly available. We used our tool to analyze different cryptographic libraries, and we found and fixed 2 critical vulnerabilities in OpenSSL, which were previously unknown. Also, we were able to analyze interpreted code, PyCrypto, where we too found leaks. Okay, now let's have a look at how data works in practice. So we have 3 consecutive phases. The first phase analyzes the program to find irregularities in the memory access patterns. These are called address differences. The phase 2 asks the question, is it actually a leak? The program could be non-deterministic, for example. So we test all address differences for this secret dependency. And the phase 3 then asks the question, how severe is a leak in practice? So we try to quantify the information loss under certain leakage models. So let's have a look at the first phase. How does it work? Well, we execute the program multiple times with different secret inputs, with different keys. And then we record so-called address traces containing all memory accesses. And if the address traces are the same, there was no leak visible. However, if they differ, we found a potential leak. And we can report it back to the developer. So let's go through the steps again. We use multiple different keys, which is important to explore many different program paths. And this ensures that we can lower the false negatives. In practice, we even observed that for symmetric ciphers, 2 to 3 keys are enough. So 2 to 3 executions are enough because symmetric ciphers do not have control flow leaks. And for asymmetric ciphers, we used 10 traces. Then we used a binary dynamic instrumentation framework to record all control flow instructions and all memory accesses. This ensures that we capture all kinds of address leakage. And in the end, we use a sequential comparison algorithm to compare the traces. And we do this pairwise for all pairs of traces we recorded previously. And this comparison tries to find these irregularities. And special care has to be taken for control flow leaks, because here the control flow diverts into multiple branches. For example, into the functions left and right from the previous example. So in this case, we have to find the point where the control flow leak is over and the two traces merge again. And we have a special trace realignment algorithm, which you can read up in the paper. Okay, and by doing so, we can find all leaks which are visible in the execution traces. However, not all address differences are actually secret dependent. But they might stem from non-determinism, as we heard before. And now my colleague will tell you what to do in this case.
All right. So once we have those address differences from the first phase, we advance to the second phase called leakage detection. And what we do here is we again start an instrumentation, so a trace recording phase. But this time we only look at the differences that we found earlier. So we are a lot faster, and our traces are a lot smaller now. In contrast to the previous phase, what we do is we execute the program with two different input sets. So one fixed input and a number of varying inputs. So let's suppose I want to take 100 measurements. I would execute the program 100 times with fixed input and 100 times with 100 random distinct secret inputs. And this gives me two different two different trace sets. And these trace sets are the input to the what we call the generic leakage test. So what the generic leakage test is doing basically is it's iterating over all the address differences that we found in phase one, and then it's looking into these two different trace sets and extracting all the addresses that we see. For instance, one instruction, let's say a difference makes a memory access, then we record all the addresses of that instruction and we build address distributions. So in the end, we have, for every differences that we detect, we have two distributions. And these two distributions we then compare with a statistical test. And if those two distributions are not similar, so do not stem from the same base distribution, we know that this is an information leak. So the reason behind is if I change my secret input and if I observe a different address distribution, then I inevitably learn something about my secret input. The problem is I'm not really sure like how much I learn or how critical that leak actually is. So this is why we also introduced the third phase that will give us this insight. So, but first we accumulate all the leaks in an intermediate report, and then we advance to the third phase. So in the third phase, we do a two-step preparation. Starting with, again, we take a look at the trace set based on the random inputs. And instead of building address distributions, we simply list the addresses that we see. So for instance, one instructions may access addresses 4, 5, 6. And the second step would be we take the corresponding secret inputs that produce the traces and plug them into a leakage model. So a leakage model is known from sidechain literature. It's basically a reduction in input space complexity. And it can be, for instance, I only consider the first byte of my secret value or one single bit or the Hamming weight. And the leakage model is in some ways domain specific. So of course I have to check for something that I do not want to leak in the addresses. So let's say in a general case, maybe the byte leakage model makes a lot of sense because I do not want, for instance, the byte values of my secret key or the byte values of my password to show up in the addresses. So let's say I choose a leakage model, one particular bit of my inputs. I may get these outputs all ones. And what this gives me essentially is a list of observation pairs, basically. And these pairs we then plug into what we call a specific leakage test. So it's a bivariate relationship test. And it simply tells me if there is any linear or nonlinear relation between those two sequences. And in this example, for instance, our test would probably say no. So if I take a look at the addresses 456, I do not necessarily learn anything new. However, if I change my leakage model, let's say, for instance, to the byte values of my secret, the sequence would change as well. And our specific leakage test would say, okay, yeah, now there is a clear linear relation between that. And this means that the leakage model, in this case, directly gives us the information that we lose from this leak. Now to finish this phase, we test all the address leaks that we found previously with all the outputs of the leakage model, and we augment the leakage report that we had from phase 2. So note that we do not drop any leaks here, so all the leaks still show up in the final report, but we have some additional information that helps us to prioritize the leak and determine which one is more critical than the other. So let's take a look at some practical results. We use data to analyze OpenSSL and PyCrypto. We found a set of, or confirmed a set of known leaks, so a lot of symmetric Cypher implementations still use lookup tables. Those leak heavily, triple dash, blowfish, Camilla, cast. So a lot of examples that still leak. There are some protected implementations for AES, of course. Still, we found that in the AES bit-sliced implementation, the key schedule itself is vulnerable because it also uses lookup tables. And the ECDSA implementation, OpenSSL, still uses a vulnerable WNAF point multiplication function, which has been noted previously and has already been exploited. Next to the confirmed leaks, we also found some new leaks. For instance, in DSA, we found a bug that omitted a constant time modular inversion during key initialization. So this is where we found quite a number of leaks. And also in RSA, we found a similar bug that also omitted a constant time modular exponentiation function and instead called a vulnerable variant. We also found a substantial number of leaks there, despite the fact that, for instance, RSA introduces quite an amount of non-determinism, for instance, stemming from the randomization in base blinding. So I have to query random numbers, I have to gather entropy, and this causes, for instance, in the execution, a lot of differences that are not critical or are not directly related to the secret key. But we filter that, data automatically filters that, and we still revealed those two bugs that we also reported to OpenSSL, provided patches, and that has been already fixed. For AES-NE and all the asymmetric keys we loaded via PEM files, we found that the key parsing function that converted hex strings to binary format also heavily leaks the key. So previous tools may not have found this because they didn't analyze the entire program execution from start to end. But with data, this is no problem. This is why we found those leaks in our analysis. To give you some performance numbers, so basically data scales with the number of leaks or the number of differences that I have to analyze. So leakage free implementations are done in a couple of seconds, and RSA with quite a number of way above 2,000 differences that we had to analyze still is below 4 CPU hours, below 4.5 gigabyte of RAM, and below 1 gigabyte of storage. All right, that already brings me to the conclusion. So data is a tool that helps you find address-based leaks, leaks that can eventually be exploited via caches, DRAM, or other microarchitectural units. We provide statistical guarantees to reduce the number of false positives and also deploy a number of strategies to reduce the number of false negatives. And we also provide a way to prioritize leaks based on leakage models. We design data to provide some benefits for developers and analysts. So it is automated. We don't need to annotate anything. We don't need the source code. And once we start data, it processes through and gives us the final report in the end. It is rather efficient, so we can actually analyze interpreted code such as Python and stay well within the range of commodity hardware. And it is also practical. As we showed, we found new vulnerabilities in OpenSSL not discovered so far. Data is still work in progress, so we're designing and implementing to improve usability, a graphical user interface, some performance improvements. We're also happy about any like remarks or ideas or features that you would wish for in a tool like Data. And for this reason, we made Data open source, so you can download it very soon from the given GitHub URL. And with this, we thank you for your attention, and we are happy to answer any questions.
Hi, I have two questions. One quick question. Did you try to get the secret key, or which extent you are saying that there is a leak?
Sorry again, I didn't quite get that.
Did you try to find the secret key?
So you mean, did we actually try to...
Actually extract the key?
To attack, so to mount an attack, to actually mount an attack, if you tried that. No, so as far as I know, no, we haven't tried that.
Okay. So my question is, for this type of attack, vulnerability for the environment of the address space randomization ASLR, will it be affected? How effective it is?
Yeah. So I mean, since we are in an evaluation context, so I want to like evaluate my own software. It's not a problem to turn off ASLR, and this is what we did for the analysis. But this is to find the problem, right? In practice, ASLR might be another obstacle that an attacker has to overcome, but it doesn't change the fact that there's a problem in the software that needs to be fixed.
Yeah. From your paper, I have seen that you basically turn down the ASLR, but you evaluate this approach to the Xeon processor using modern compiler, and most of the modern compiler enforce the address space randomization. Even Intel's basically do that. So how can you justify this approach by turn down your ASLR?
So I mean, if I understand it correctly, you say that there is like software out there where I cannot like turn off ASLR and I have to live with that in the evaluation. Is that correct?
I mean, basically ASLR is enforced for all modern compiler and also the processor do that. So we are doing some sort of attacks which we are turned off the ASLR. So how can you justify? I mean, what is the real application for that? This type of attack can happen because I will turn on my ASLR.
So just to clarify, ASLR must not be turned off on any like running or production system. So we only turn it off for the evaluation of the software. So that's it. So once we find the leaks, you can like deploy your software on systems with ASLR. So there's no like connection or relation at all.
Okay, thank you.
Yeah, so our approach is really to find leaks in the source code. So we give developers an aid to find the leakage, and therefore we try to reduce any noise from the operating system so far that we really can pinpoint the leakage origin in the source code. In practice, attacks might be harder to do different CPU architectures and all this stuff, but we really want to find the problems in the source code. Yeah.